Imagine taking a commercial flight from New York to London, and upon arrival, the airline permanently scraps the Boeing 747. Global travel would be economically impossible. Yet for 70 years, we accepted exactly this premise for getting to space. Historically, rockets were multi-million-dollar single-use vehicles. Even the space shuttle, which was billed as a reusable system, relied on massive solid rocket boosters and a colossal external tank that were jettisoned and severely damaged just minutes into the flight. The parts of the shuttle that did return to Earth required thousands of hours of intense manual labor. Technicians had to individually inspect, repair, and replace the fragile ceramic heat shield tiles one by one before the orbiter could safely fly again. Rebuilding a vehicle is slow and astronomically expensive. True affordable access to space requires the aerospace industry to stop refurbishing rockets and start treating them like airplanes, landing, refueling, and launching again immediately. This cutaway shows the internal plumbing of a traditional rocket engine, highlighting the primary physical barrier to rapid turnaround: soot. Burning kerosene leaves a sticky carbon residue that progressively clogs the engine's intricate plumbing and fuel injectors. In addition to the soot buildup, engines face a severe thermal tax. Launching into orbit and re-entering the atmosphere subjects metal turbines and structural joints to thousands of degrees of heat, slowly warping and weakening the components every single time they ignite. SpaceX realized that tweaking their existing Falcon 9 hardware could not physically overcome these limits. Achieving airplane-like operations required a clean sheet design, a new ship, a new booster, and entirely new engines built specifically to survive extreme, repeated thermal and chemical cycles. The resulting Raptor engine was engineered specifically to solve the soot and heat constraints. This new architecture was a strict prerequisite for making sustainable spaceflight a reality. The first major architectural shift with Raptor was the fuel. SpaceX abandoned kerosene entirely and switched to liquid methane. Methane burns incredibly clean, leaving the engine's internal components pristine and free of carbon buildup even after a prolonged firing. This diagram shows the engine's full-flow staged combustion cycle, designed to manage extreme heat. Instead of wasting propellant to power the engine's pumps, both the liquid oxygen and the liquid methane are completely converted into hot gases before entering the main combustion chamber, driving the turbines highly efficiently and keeping internal hardware temperatures manageable. Because these gases are precisely controlled, the Raptor engine can safely shut down in the vacuum of space and then relight reliably in the thick, turbulent atmosphere right before landing. The combination of clean fuel and precise thermal control eliminates the need for a total engine teardown after touchdown. A ground crew can inspect the vehicle, pump in fresh methane and oxygen, and prepare for another launch within hours. By solving the internal chemistry and thermodynamics of the engine, SpaceX removed the absolute hardest physical barrier preventing a high-frequency route to Mars. Designing a perfect engine on a computer is very different from flying one. Once you subject these complex systems to the chaotic vibrations of an actual launch, digital simulations eventually fail to predict where hardware limits truly lie. To bridge the gap between theory and reality, SpaceX relies heavily on a test-like-you-fly philosophy. They treat every launch as an opportunity to push the hardware until it breaks, gathering the real-world flight data needed to quickly fix weak points. The lineage of this approach is highly visible in the early days of the Falcon 9 program. For years, SpaceX sent boosters plummeting back toward ocean platforms, heavily gathering data from spectacular explosions as they dialed in the algorithms. Today, those early violent failures have translated into absolute routine. We regularly watch 14-story boosters return from orbit, deploy their landing legs, and touch down perfectly on target. That exact same aggressive, iterative cycle is playing out right now in South Texas with the massive Starship vehicle. They are flying fully integrated ships, deliberately testing novel booster catch mechanisms and experimental heat shield configurations to see exactly what survives re-entry. Between the 3rd and 10th flight tests, SpaceX engineers compressed years of traditional aerospace development into a matter of months, iterating on valves, updating flight software, and engine performance at the fastest pace in heavy lift history. The fire and smoke currently rolling over the Boca Chica launch pad is the sound of the engineering bottleneck physically breaking apart. An engine capable of rapid reuse dictates exactly what humans can physically accomplish in space. This chart shows the payload capacity of every active rocket globally, compared to the singular requirement for a sustainable Mars colony. The discrepancy is what engineers call the mass gap. Transporting millions of tons of cargo to another planet is mathematically impossible if you throw away the delivery vehicle after a single trip. A fully reusable architecture changes the physics of the equation. If a single starship loops back and forth from orbit hundreds of times a year, that solitary vehicle can eventually transport more mass than the rest of the world's rockets combined. The human element is already integrating into this capability. The Polaris Dawn and commercial crew missions put astronauts directly into vehicles built on this foundation, living and working within an entirely new operational framework. The explosive tests and engine static fires happening today provide the required physical infrastructure for tomorrow's orbital economy. Treating rockets like airplanes solves the mass and economic barriers of deep space exploration. We are permanently opening the door to the stars.